Alright, this is the companion for Chapter 18. We'll start with sections 18:1 through 4. This introduces us to some concepts that will be important for understanding electrical circuits. We'll start by talking about batteries. A battery, the symbol for it is like this, and what it does is supply a constant potential. The potential is due to a chemical reaction that happens inside the battery, which places positive charges on one electrode and negative charges on the other. So the book says that a battery is not a source of constant current. Well, it is if you have a constant resistance, but if you change the resistance, then there will be a new amount of current that flows. Here's the equation that you use. The battery can supply a constant voltage. If you increase resistance, then the current goes down. So if you look on the side of a battery, it's not going to tell you how much current it provides. It's going to tell you the voltage that it will keep this side of the battery relative to this side of the battery. The book mentions something called EMF, or electromotive force. We now know that you might as well just call it voltage. We call it voltage everywhere. We already had another name for it, potential, and it was confusing enough. Why add another one? I'm never going to use EMF, or electromotive force. In the battery, I use, as a model, so let's call this the positive terminal and the negative. I use something that I call V internal and R internal. So here's R internal, here's V internal. So instead of EMF, I like to use that notation. And the terminal voltage, this is the useful voltage that you get at the terminals, is equal to the internal voltage, but we're missing some of the voltage, and it's equal to I times R internal. So if no current flows, this is 0, and the terminal voltage is equal to the internal voltage. But once you start driving a current using the battery, then this resistor inside, there's not really a resistor, but this model resistance inside will start using some of the energy of the charges, and you don't get all of the internal voltage at your terminals. I defined current this way. This is called Ohm's law. Usually you'll see it written V equals IR. The reason I write it this way is because it reminds me that current is just the effect. If I apply a bigger voltage, then current will go up. If I apply a smaller voltage, then current goes down. They're proportional, and the constant of proportionality is 1 over the resistance in the circuit. Current is defined as the amount of charge that passes in a given amount of time that passes. So if we were to come here on this picture that I've drawn of a battery and add a little resistor so that now current can flow, then you'll have electrons that go up this wire through the resistor like this. Now this is electron current. Normally we talk about conventional current, which actually flows from positive to negative. It's just an unfortunate accident of history that they decided to call positive current that direction. So even though the charges that are actually moving go in this direction, we call the current, it's as if positive charges are moving this way, because the actual moving charges are negative. Now, when I write a resistance up here, you might wonder, what is this circuit? I mean, why are we always drawing a battery with a resistance? Well, this can be a resistor. It's not as useful as if it's something else. For example, this R might be a light bulb, and the current flowing through it is dumping its energy into that light bulb as heat. So the filament of a light bulb. The light bulb heats up, it gives off light to get rid of some of that energy, and so even though we called it a resistor, it's just kind of it's like a placeholder for anything you could think of. This could be an LED, although it would have a different picture in the diagram. It could be a motor It could be anything that uses electrical energy to do something useful for you. We don't just go and hook up resistors in circuits, except in physics, because we want to study the way the current changes as you change voltage. If you sat here and counted how many charges pass per second, and you measured the total charge in coulombs, then that's how you plug it into this equation and you get the current out. If, say, 3 coulombs passed in the 1 second that you were counting, then that would be 3 coulombs divided by 1 second. That's 3 amps. This is a new unit called amperes, and that's really what it means, that 1 coulomb per second passed. So 3 times that means 3 coulombs passed in a second. There's another thing that you can tell from this equation, and that is that if 1 amp equals 1 over 1 ohm times a volt, then you know that 1 ohm is equal to 1 volt divided by 1 amp. And that's useful because this ohm is actually made up of a bunch of different things. Remember, the volt is a joule per coulomb, an amp is a coulomb per second. You can multiply those out, expand the joule into base units, and find out what an ohm is. It's something kind of nasty. If you want a really concise explanation of what's happening with the energy of these charges as it goes through a resistor, reread the section called Some Helpful Clarifications on page 500. It is extremely useful. It gets to the core of the issues. It's only, I think, 3 paragraphs or something, but read it, reread it. If you understand that, you will basically understand how current flows through resistors and through the other things that we'll study. One of the things it says is that charge does not get used up in a resistor as it flows through it. To illustrate that, let's think about, okay, here's a battery. It gives some charges, some potential energy, and I'm going to use my favorite analogy of a Plinko game. Okay, these are nails in the Plinko game. They represent defects in the crystal of the conductor. And when an electron flows, all right, I'll draw it the right way. See how the electrons leave the negative terminal and enter the positive terminal? The electrons want to get to the top of this Plinko game, so they come this way to start playing, and they will hit one of these nails and bounce off the nails on their way up to the top. So this is the way the electrons will go. There's an electric field in the resistor that accelerates them in the up direction. So let's just draw that. E is this way, and the force, if you remember, is Q times E. That's a vector equation. We've got a negative scalar for the charge on an electron, multiplied by an E field in this direction, and the force is in this direction. So E field accelerates the electrons after it has these collisions with the nails. Now in each of these collisions, the electron is giving up some energy, and this is what goes to heat up the resistor. So in a light bulb, this is useful because this kinetic energy that the electrons are giving these defects in the crystal get added up to heat up the resistor and then give off light. There are lots of these electrons playing Plinko as they bounce their way through this game that is the resistor. And so what you find is that as many electrons flow through the resistor are replenished at the negative end of the resistor. You never have a buildup of static charge. The charge doesn't get used up. What does get used up is the electrostatic potential energy. Remember, this electron, you can think of it as being at the top of an electrostatic potential energy hill. It wants to get to where the positive charges are over here on the positive terminal. And so they will roll down this Plinko game hill to get there. When they make it back to where the positive charge is, they have lost all of the potential energy given to them by the battery. That's what gets used up as current flows through a resistor, the electric potential energy. All right, the last thing that we want to explain from these sections is how to calculate the resistance. So resistance, the formula for it is resistivity times the length of the resistor divided by the area of the resistor. The resistivity has to do with the number of these nails and also how dense the electrons are in the material. Because think about this, right when I apply the voltage to the resistor, it tips the entire Plinko game, and there were some electrons that were already inside the game, so they started here and played their own little game to get out. The electric field gets set up everywhere inside the resistor at the same time, and so the density of charge carriers also comes into play, and it's here in the resistivity. So I'll circle it with yellow and with orange to remind us that this is about the number of nails and the number of carriers to carry the charge. Now the length is just the length of the Plinko game. And if you remember, the electric field depends on how much distance you have to drop the voltage. It equals delta V over delta X. There's a minus sign in there because it points downhill. This delta X is the length of the resistor. So I'll circle that in blue here. And the area determines how many of the electrons can enter the game at the same time. So if you double the area, twice as many electrons can play at the same time, and the resistance goes down by a factor of 2. So there's the formula for the resistance of a resistor. This you look up on a chart. This one deals with how long it is, so you can just measure it, and this one is how thick it is, the cross-sectional area, so you can also just measure that. Let's go on to section 5 through 7 of chapter 18. This deals with power, and it says the power, well, this is kind of a reminder, it's the work done per unit time. And you may remember that as a charge rolls down a potential hill of size V, so let's say we've got this box full of charge. If it rolls down this hill, the amount of work done by the electric field here is equal to Q times V. So let's rewrite this as Q times V over T. This may look familiar from the last section that we were looking at. This is just current. Okay? Q divided by T. So we've got Q divided by T times V. Well, that's just current times voltage. That's pretty special. One thing that tricks people here, though, is they forget that the current depends on the voltage. Ohm's law hasn't gone away. So if you double the voltage on a resistor and you want to calculate the new power, not only does this term double, so the voltage doubles, but this is equal to 1 over R times V. So this also doubles. Okay, doubling the voltage across a resistor actually increases the power dissipated by the resistor by a factor of 4 instead of 2, as you might be led to believe by just looking at I times V. A better way to write this, to remind ourselves, is that I is a function of V times V. So the power is the current times the voltage, but changing the voltage will also change the current. So in this case over here, the power is V squared over R. That's the one you would use and not have to worry about that I is a function of V. You've already included that here. So if you wanted to calculate the total energy used by a resistor in a time, the energy is power times T, Remember, work and energy have the same units, and they're very similar. Work is defined as the energy put into a system. Work done on a system is defined that way. And so if you want to know the energy dissipated by a resistor, for example, you look at the power used up per second. So the energy used up per second. You look at the power, which is the energy used up per second, times the time. That gets rid of the per second, and you get the total energy dissipated. All right, one more thing that was discussed here are fuses. What you do with fuses is you put them in a circuit, and they protect the parts of a circuit from having too much current pass through them. So the fuse might be designed to break at, let's say, 10 amp. So 10 amperes. That means that if ever you have 10 amps flowing through this fuse, this is kind of what they look like. They're just a piece of metal with a wire that goes and connects the two ends, which are made out of metal. Another way you see them, you might have two metal caps, and they're inside a piece of plastic. This is what car fuses normally look like. And then again, there's this piece of metal or a wire that connects them. This wire is designed to only take as much current as the fuse is rated for, and then it will burn out if it goes higher than that. So this can let 10 amps flow through it, but if 11 amps flow through it, then the wire burns up and it breaks the circuit. The reason being, you might have something further on down the circuit that can only take, say, 12 amps max. Well, the 10 amp fuse will protect that, because if it ever gets above 10, this wire will burn out, and you'll know that you'll never reach that maximum current that say your car radio or something is rated for, or your headlights, or whatever it is. We have the same kind of thing if you've ever seen in your house the circuit breaker box, and they'll have a bunch of switches that are switched to on. If too much current ever flows through one of these circuits, each one is on its own circuit. If you tried to plug too many things into one circuit, the circuit breaker will trip, and it moves this to about halfway over between off and on. That's how you can tell which one tripped. And you can reset it by switching it to off and then back to on. That's a circuit breaker. Again, both of these are just designed to protect circuit elements. In this case, it's more to protect the wire, because if too much current flows through the wires they have running through your walls, then they can melt the insulation and cause fires. So this is why electrical code requires that you have circuit breakers on the wires through your home, so you don't start a house fire that way. The last part of section 18, 5 through 7 that I wanted to discuss was alternating current. And the book had a lot of equations that you don't need to worry about. The important one is that the average power is the RMS current times the RMS voltage. Again, remember that this is a function of V. So if you increase the RMS voltage, you will also increase the RMS current. Alright, and the other thing you need to remember is how to calculate RMS. For sine waves, IRMS or VRMS or anything RMS, if it's a sine wave, is just 1 over the square root of 2 times the maximum that it ever reaches. If this is 0, this would be I naught up here at the top. Just in case it's been a while, 1 over the square root of 2 is about 0.71 approximately.